This is Dr. Holt. This video is on simple harmonic motion. The objectives of this video, when you complete it, should be you should understand common terms about harmonic motion. You should understand when the restoring force is maximum and zero, and when the velocity is maximum and zero, as well as the acceleration, and how to use calculus to derive your motion equations, and then how to solve simple harmonic motion problems. The word oscillate means to swing back and forth. Oscillation occurs when a system is disturbed from a position of stable equilibrium. Many familiar examples exist. These include surfers that bob up and down waiting for the right wave, clock pendulums that swing back and forth, and strings and reeds of musical instruments that vibrate. A common, very important, and very basic of the oscillatory motion is the simple harmonic motion. Now, simple harmonic motion is repetitive motion back and forth from an equilibrium position where the maximum displacement on either side of the equilibrium position is the same distance. We'll come back to or review that Hooke's law. We've talked about this in previous lecture, but the net force is going to equal to the spring constant times the displacement. And the reason we again use the minus is because the force is going to be opposite direction of the displacement. If I move this object to the right, the force is going to go back the other direction, so that we set that equal to minus k. Now we also know that net force is always equal to max of the object times the acceleration, so we can set those equal to one another. So we could solve for the acceleration and divide both sides by mass and say it's equal to minus kx divided by mass. We also know that the acceleration of an object is equal to the second derivative of the position equation in respect to time. So note that in a simple harmonic motion, the acceleration and thus the net force are both proportional to, but in opposite direction from the displacement from the equilibrium position. In these 5 pictures here I have, in this example, I have maximum net force to the left. I've displaced the object to the right. I will have maximum force going back to the left here. Now in these cases, I will find out at this point I'm going to have maximum acceleration. My velocity is going to be 0. When I displace it to the right, my acceleration is going to go back to the left. In this example here, I'm going back through my equilibrium point. I will reach my maximum velocity. Now they make this, again, the reason this is negative only because I'll set up my axis system. Anything to the right is positive. So my maximum velocity will be going through the equilibrium point, and my acceleration at that point will be 0. When the object compresses the spring, again, I will reach maximum acceleration going back to the right, and that is a result of my net force going back to the right. And in these positions, my velocity will equal to 0. And this little table here, very similar to the previous slide. In this case, I have the object a maximum displacement to the right, and notice here again my position's max, my acceleration will be max, be going to the left, and my potential energy of the spring system will also be being max because I got the maximum displacement. When I go back through the equilibrium point, my position is 0, I'll have maximum velocity, my acceleration will be 0, but now I've reached the maximum kinetic energy. Because I have maximum velocity, I have no spring potential energy. When I go back to the left, again, I've reached my maximum displacement. We're going to let this be negative because I've set up anything goes to the right to be positive, anything to the left negative. I reach my maximum acceleration, is going to go back to the right, and the potential energy is going to be maxed. In setting up your simple harmonic motion equations, we can use its position is equal to A, the amplitude, the cosine of omega t, plus your phase constant, or we can set it up as A sine omega t plus the phase constant. Simple harmonic motion systems are typically used or set up using these two equations. The reason being is because the oscillation follows a trig function that resembles a cosine or a sine function. Now, a couple terms that we need to know, the first one being the period. Now, the period is going to be the time it takes an object here to be, say, pulled back, released, and go all the way up and all the way back. That is the time, what a period is. It is not the time to go from here up to the other extreme. It has to make one complete oscillation. So we define that as period. And period is noted with the symbol T, and is typically going to be the units in seconds. Again, it doesn't have to be, but that is what it usually is measured in seconds, the time it takes to go one complete oscillation. Omega, it represents how many radians I travel per second. And that is called the angular frequency. So if I release it and it goes all the way up and all the way back, I've traveled a distance of 2 pi radians. So again, if I know what my period is, then I can find my angular frequency because I know I've traveled 2 pi radians in that amount of time. All right, the other part of the equation is going to be the phase constant, whether the object is going to be like pi over 2 out of phase or a phase constant because 0. One of the things I'm going to recommend to you is that if you're modeling these systems and I pull the object back and release it, and I release it at time equals 0, then your equation is going to be easier if you model it like this, as your position is equal to A, your amplitude, meaning how far you displaced it, times the cosine of omega t. If you can keep it simple like that, it's going to be much easier for you to set that up. Again, it can be modeled with a sine function, but remember, if you pull it back at time equals 0, and you need to get maximum displacement or maximum position, then you're going to be pi over 2 out of phase. Again, as noted, as I just mentioned, you can be in phase or out of phase. If the phase difference is going to be 0 or an integer times 2 pi, then we can say the system is in phase, meaning one object can be released at, say, 4 seconds before another object, as long as they are moving in phase together, and even though the time difference is different, we say they're in phase. If one object is moving down as another object is moving up as they're going through the equilibrium point, then we can say they are in phase. All right, going to get into a little bit of calculus here and talk about how to derive your velocity as well as your acceleration equations. Again, we start with the basic equation of my position is equal to A times the cosine of omega t plus my delta. I will take the derivative of my position equation, and again, I have to do that using the chain rule, and here I will get my velocity as negative omega times my amplitude times my sine of omega t plus delta. That will give my velocity at any point. As far as the acceleration, I will take the derivative of this, again using chain rule, and I will get minus omega squared A cosine omega t plus delta. Now note here that this value right here is exactly what we had here. So if I just substitute back in x, I can say the acceleration at any point is going to be equal to negative omega squared times my position. That's going to tell my acceleration at any point in time. Other thing I want to do is to prove this equation here. Again, we mentioned earlier that acceleration is minus kx divided by mass. if I set this equal to here, as I did right here, and solve for omega, then I can say omega is going to equal to the square root of the spring constant divided by the mass that's attached to it. If I take the square root of that, I can immediately find what my angular frequency is going to be. All right, if we go back again to the two equations, the velocity and the acceleration, and let's talk about how to find the maximum value. Now we note the range of the sine function, the cosine function is always going to be plus or minus 1. So if we let this be maximized to the far values of the range, being the positive ones, and let this again just approach 1 and approach 1, then we can find V max as always going to be omega times alpha. Again, it's noted here as negative only because of direction. If I substitute back in for omega, which we said is the square root of k over m, I can always find V max again as two ways: omega a, omega times amplitude, or the square root of the spring constant divided by the mass times amplitude. Or my maximum acceleration will be omega squared times amplitude, or km times a. That's going to give me my maximum velocity and my maximum acceleration. All right, and I noted it here earlier as the period is 2 pi over omega. Again, I can substitute back in for omega, and we said omega was equal to the square root of k over m. Let me go back and just show you where that was. What I did right here is I substitute that back in to right into here. Again, that's going to inverse this. That's going to give me period. Well, we get a 2 pi times the square root of mass divided by the spring constant. Again, we know frequency is 1 over the period, and we can come back to this equation right here too to find the frequency. So if you want to find the period of your system, as long as you know what the mass is and the spring constant, you can find the period, as well as you can find the frequency as long as you know the spring constant and the mass. Let's get into working a problem or two. In this example, I have an object that's going to oscillate with a simple harmonic motion along the x-axis. Its position is given by the equation of the amplitude, which is the 4 centimeters, times the cosine of omega t plus pi over 4. We're going to have a phase constant here. We want to determine what the amplitude is. Well, obviously I hope that the amplitude would be very easy. That's going to be this value right here. So we know immediately that the amplitude is going to be equal to 4 centimeters. All right, determine what frequency is. Well, first thing I'm going to do is I'm going to just find period. Again, I know that period t is going to equal to 2 pi divided by omega. So it's 2 pi here. Omega, again, is this value right here. I divide by pi, and I get immediately what my period of my system is going to be, and that's going to be equal to 2 seconds. Okay, I know frequency is going to equal to 1 over my period. So that's going to be equal to 1 over 2 pi, or sorry, 1 over 2 seconds. And that's going to give me a value of 1/2 or 0.5 hertz. Frequency is going to be measured in hertz, and that's how I get the frequency. So here we are able to determine what the amplitude was, the frequency of the period from just this equation. All right, let's go ahead and move on. I want to calculate the velocity and acceleration at any time interval. All we have to do now is take the derivative of this. Again, we'll use the chain rule, and I will get my velocity is equal to okay, I'll work through the whole thing, 4.00 centimeters. We take the derivative of this, which is going to give me a negative sine times what's inside of pi t plus pi over 4. We will take the derivative inside here, which is going to give me the value of pi, and I will end up with the velocity equation is equal to minus 4 pi, again that's units will be in centimeters here, times the sine of pi t plus pi divided by 4. Again, those units will be in centimeters per second. I'll go ahead and take that out right here since I'm putting the units at the end. That will give my velocity from using just the position equation. And now if I want my acceleration is going to be the derivative of this. And again, I'm not going to go through all the details of how to do the chain rule. I'm sure you can figure that out. And when I get that value, I will get minus 4 times pi squared times the cosine of pi t plus pi over 4. Again, I can substitute back in my x value and I get my acceleration is equal to negative pi squared times my displacement, and again the units of that will be centimeters per second squared. So we were able to determine the acceleration from either one of these values here. Okay, we would use this one when we want to know what the time would be, or when we know what time is, and we would use this for the velocity when we know what time is. If we know the position, we could come back and use this equation here. Alright, so we were able to determine what the velocity and acceleration would be at any time interval. Let's move on here. Now we want to determine the position, velocity, and acceleration at 1 second. All I have to do again is just to substitute back in this equation for t is equal to 1, substitute back in this equation for t is equal to 1, and the acceleration as t is equal to 1. If you do that, I believe I can go ahead and work it. Let's work it in detail. Oops, I'll do this in blocks, sorry. That the position is going to equal to the 4 centimeters. We'll let that be 1. That's going to give me pi plus pi over 4. That's going to give me the cosine of 5 pi over 4. Now from the unit circle, we know that the cosine of 5 pi over 4 is negative square root of 2 over 2. So we could say the position is going to equal to the 4 centimeters times negative square root of 2 over 2. That's going to give me a value of negative 2, the square root of 2 centimeters. That would be my position at 1 second. Now to find the velocity, I go back to the equation that we generate right here. I will put t in as 1. Again, I will not go through all the values, but you will get 2 pi times the square root of 2, and that would be in centimeters per second. And the acceleration, again, I will use the equation previously right here. I will substitute in t as 1. I will get 2 times the square root of 2 pi squared times centimeters per second squared. Alright, so we were able to determine what the position is, the velocity, and the acceleration of t is equal to 1. If you want to maximize, again, we just come back and use these equations. We just substitute back in our amplitude of 4. We can determine what the spring constant is if we need to. We know here we'd probably just be simpler just to use this because we can find omega very quickly. And we know, again, as mentioned, omega we figured out was just going to be pi radians per second. Again, that's nothing more than 2 pi divided by the period. We can put that back into the equation. We can find that the velocity max is going to equal to 4 pi centimeters per second. And we can find out the acceleration max is going to equal to 4 pi squared centimeters per second. Okay, very valuable equations to use as far as these right here to find maximum velocity, maximum acceleration. Alright, to determine then what the displacement of the object between 0 and 1, again we're looking for the displacement, not distance traveled. All we'd have to do is put in 0 here, find out my position, put in 1 here, find out my position, and I would know the displacement between 0 and 1 second. Alright, here's a problem that I'll put up. You're welcome to work this on yourself. I would just freeze the video, read it, and then go ahead and answer all these questions. I put up the answers here on this next slide if you want to go back and double check it. But it's a good way for you to practice what I've discussed in this lecture. As always, as you work these problems, I wish you the best of luck. Again, refer back to this video as needed as you solve. And again, when you're setting up your own modeling at your systems, if you're pulling back an object, again, I highly recommend this. When you pull back an object and release it at time equals 0, that you model this with a cosine function and not a sine function, and ignore your phase constant. It's just going to make it simpler for you guys. All right, again, best of luck.